So we know Vapnik was interested basically in approaching zero with this generalization term and also reducing as much as possible, I will write like this empirical risk. That was the objective. He decided to start looking for techniques he could use to find that result. And the best technique was, or the best tool, was the law of large numbers. What the law of large numbers says, basically, is I have the probability of some divergence of an average value given some variable, some C variable, from 1 to n, and that approaches the expected value of that variable in terms of some epsilon according to an upper bound defined by Chernoff, which was next extended by Hofding. And that bounds like 2 times the exponential value of minus 2n epsilon squared. And this is quite useful because here I have some important stuff. At first, this guy here is an average, and that's very close to the empirical risk, as you guys can see. Actually, it's the same thing if this C value for all possible I, if they are defined in the interval from 0 to 1. That's exactly the same. So if it is defined in that interval, we can ensure this bound, and we have this as a tool we could use. Yeah, Vapnik used that basically. But there are some and this guy is the same as the expected risk. Expected risk. But he had like some problems to use this guy. At first, the first problem is, as usual, yeah, we've got like so many problems. The first problem is this is possible to be used if and only if, and this is one of the most important stuff here, data is identically and independently distributed. So if it's not, you don't have any upper bound. You can't ensure anything. So we've seen like many people using machine learning, supervised machine learning, in the context of problems where you have some sort of temporal dependence. That's not valid. We don't have like any sort of tool to ensure learning in those conditions. We could come up with tools for that, but we still don't have it. Don't have those, right? And there is another limitation, which is this is valid since we've got a function that was selected independently from the data set. Independently from the data set we have. For example, in this case, if I decide to use an average, is that okay? Yes, because I didn't select the average based on the data I have. But in machine learning, we do that. We've got like algorithms which are driven by convex functions, and we are looking for the best solution based on some sample we have. So we've been driven by some sort of sample or data set we've got, and that's not valid in that situation. And that's a problem, again. So somehow Vapnik had to come up with a solution. And there's a third, I forgot about this third, which is the data distribution. The data distribution must be static, fixed. This is very important. For example, if I have like a normal distribution, afterwards the mean of that distribution could be 0, and afterwards it's like 0.2. It's not the same. so it's not valid anymore. This is only valid if we still have the same data distribution. And that's meaningful, and important. Why? Because basically we are talking about an infinite amount of data we expect to receive, we expect to sample, and somehow we expect to represent the expected value by collecting samples. And if the distribution changes, how can I have such sort of approximation? It's just impossible, right? So these three conditions are very important. Data must be IID, distribution must be static, and the function somehow cannot be selected from the data set. And those were the first limitations that Vapnik had, and it had to deal with those limitations somehow. Before that, I'm going to show you what this is about, because I think it's interesting to see some plots. For example, if you guys look there, it's better. So this is R, right? And for example, consider I have some sample which goes from 1 to 1000, for example. This is a sequence, right? From 1 to 1000. Basically, that's what's happening here. So I'm going to plot this exponential value given -2 times n times some epsilon. Could be any kind of epsilon. Let's say I'm going to define epsilon. Let's say epsilon is like 0.1. If epsilon is 0.1, that basically means I accept a divergence in between the empirical and the expected risk no greater than 0.1. It can be like 0.09, 0.08, 0.0 something, but it cannot be equal or greater than 0.1. So if I define like that, I have the results here for all n's, and I'm going to plot that because that's helpful to understand what's happening. What's the basic idea behind this? I could use this convergence as a criterion to select sample sizes, to select the best classification algorithm, even to prove that learning is possible. That was the basic idea behind Vapnik's thoughts, basically. So he was planning to use this guy somehow. And you see, that's a bound, an upper bound for a probability term. So it doesn't matter values which are greater than 1, because probability is a bounded measure. So we are just interested in values which are below or smaller than 1. If it's greater, it's just not interesting. Okay? So on top of that, somehow we had to solve this problem. Actually, Vapnik had. The first thing he did was, okay, I cannot solve this data IID problem, so I'm gonna assume data is IID. And that's a problem, because nowadays people sometimes forget that and use data, non-ID data, and that's a problem, because you have no guarantee you are learning. You're just guessing, actually. So he just assumed, okay, I'm gonna make this an assumption. I'm gonna assume, as the mathematicians usually say, I'm gonna ask that. I'm gonna ask the user, okay, provide me something that's IID, and I carry on from that. Okay, the next stuff is how can I ensure a distribution is static? He didn't. He assumed. So he came here, and that's another assumption. Just assume, okay, data is static, and that's a problem for especially for me. For example, I work with data streams, and we've got distributions changing along time, right? We've got some sort of distribution, and that distribution is going to change along time. How can I work with some sort of learning in that condition? Because I cannot have this guy. It's just an assumption. So somehow I have to deal with that in a different fashion, in a different way. Okay, let's talk about that maybe in another context. So Vapnik had the chance to work with this, only with this guy here, only with the possibility of selecting a function. So his basic idea was I could come up with some sort of transformation on top of this law of large numbers using in my problem, basically. And he did that. He rewrote this formulation like this. That was his first step.